All right, let's jump into this paper. Stealing machine learning models via prediction APIs.
Okay.
I know you're really into this kind of stuff, so I think,
This is right up my alley.
yeah, this is really up your alley, all this math and machine learning and data science.
Absolutely.
So this paper is all about this attack, this model extraction attack, and how someone could basically like duplicate a machine learning model.
Yeah, essentially by interacting with it through a service, like an online service.
Oh, wow.
And they actually did this against real companies.
Oh, wow.
Showing how vulnerable these things can be.
Like reverse engineering
Yeah,
a machine learning model just by using it?
exactly. And to kind of set the stage, we should talk about machine learning as a service, or MLA.
Okay.
So these are platforms provided by companies like Amazon and Google and Microsoft and Big ML, and they're booming right now. They're really popular. And basically what they do is they provide easy access to powerful machine learning models. So the user doesn't have to do all the hard work of building and training these models. They can just send queries and get predictions back. So that's the service part of it.
So it's kind of like using a really sophisticated calculator where
Yeah.
you don't have to derive all the formulas yourself.
Exactly. Yeah.
But I sense there's a catch.
There is, yeah. The issue is that these companies are trying to protect their intellectual property.
Yeah.
You know, they put a lot of work into building these models. They don't want to just give them away.
Right.
And they're also trying to protect the privacy of the training data
Okay.
that was used to build these models. And so there's this inherent tension between accessibility and protection.
Oh, okay.
And that's where these model extraction attacks come in.
So someone could potentially steal a company's machine learning model
Yeah.
and all the insights that are embedded in it just by interacting with the API.
Exactly. And the motivations for doing this are varied. I mean, some people just want to avoid paying for the service.
Oh.
You know, they could steal the model and use it for free. Okay.
But there are more nefarious reasons, too, like gaining access to sensitive training data
Okay.
or using this stolen model as a stepping stone to other attacks, like evasion attacks.
Okay. Wow. That's pretty serious.
Yeah.
So how do these attacks actually work?
Well, there are a bunch of techniques that the paper explores, and it really depends on how much information is revealed by the prediction API.
Okay.
But one really clever approach exploits the fact that many models provide confidence values along with their predictions.
Can you just quickly define confidence values for those of us who might not be familiar with the term?
Yeah, sure. So imagine you ask a model to classify an email as spam or not spam.
Okay.
The confidence value would be a measure of how certain the model is in its prediction.
Okay.
So it might say, I'm 80% sure that this is spam.
I see. So it's not just giving a yes or no answer, but also giving a measure of how much it believes in that answer.
Exactly. And for some types of models like logistic regression and in neural networks.
Right. These confidence values come from continuous mathematical functions.
Okay.
And these functions have parameters that determine how the model makes its predictions.
Okay.
So by making carefully crafted queries and observing the resulting confidence values, an attacker can essentially set up a system of equations and solve for those unknown parameters.
So you're using algebra to like reverse engineer the model.
Exactly. And for some models, this is surprisingly easy.
Wow.
For example, to extract a binary logistic regression model, you only need D plus 1 queries,
Okay.
where D is the number of features.
Wow.
They even extended this approach to multi-class logistic regression and multi-layer perceptrons.
Okay.
So it's pretty broadly applicable.
That's concerning.
Yeah.
What about models that don't use these continuous functions like decision trees?
Right. That's where things get even more interesting.
Right.
They actually developed a whole new attack called a pathfinding attack specifically for decision trees.
Oh, wow.
So unlike logistic models, decision trees work by partitioning the input space into regions based on a series of decisions.
I'm picturing a flow chart kind of
Exactly. Yeah.
with like branches
Right.
leading to different classifications.
Exactly. And the path that an input takes through this tree determines its final classification.
Okay.
So what these attackers do is they use the prediction API to reconstruct the tree's structure.
Oh, wow. So they were like mapping out the flow chart.
Yeah, and they do this by using something called identity oracles.
Identity oracles. What is that?
Basically, these are functions that reveal information about the internal nodes or leaves of the tree
Okay.
based on the input that you give it.
Okay.
So by carefully choosing their inputs and using these identity oracles, they can piece together the entire decision tree.
Wow. It's like they're playing hide and seek with the model,
Yeah, kind of.
and they're slowly uncovering its secrets.
And the really impressive thing is that they tested this against real decision trees,
Okay.
trained on data sets from Big ML's public gallery,
Okay.
and they had really high success rates. So this shows that even decision trees, which seem kind of discrete and structured,
Yeah.
can be vulnerable to these extraction attacks.
So even subtle leaks of information can be exploited.
Absolutely. And this really highlights the need for some robust countermeasures to protect against these attacks.
Right. So before we get into those countermeasures, let's look at some real-world examples
Okay.
of how these attacks can actually play out.
Sure. Yeah, so the paper actually presents 2 case studies that show how these attacks work in the real world.
Okay, let's hear about those. I think real-world examples are always helpful to kind of ground these concepts.
Right. So the first case study focuses on Big ML, which is a popular molasses provider.
Okay.
And what the researchers did was they trained a decision tree model on the German credit dataset.
Yeah.
And they made it available as a service through Big ML.
So it's like a paper query kind of model.
Exactly. Yeah,
Yeah.
users can submit data and get predictions back for a fee.
Okay, typical setup for a commercial service.
Right. And then they launched their pathfinding attack against this model. And they were able to fully extract the tree structure.
Oh, wow. So they got the entire
The whole
model
thing.
without knowing anything about it beforehand.
Yep. And they also quantified how many queries it took,
Okay.
which was relatively few.
So it's an efficient attack.
Very efficient, and in a paper query system that translates to direct financial loss for Big ML.
Right, because they're not getting paid for those queries.
Exactly, and it's a potential savings for the attacker who can now use the model for free.
Wow. That's a good illustration of the real economic impact of this.
Yeah, it's not just theoretical. There's real money at stake.
So what about the second case study?
So this one targets Amazon machine learning.
Okay, another big player.
Yeah, and in this case, they were trying to extract a logistic regression model.
Yeah.
But there's a twist. They had to first figure out what kind of feature extraction Amazon was doing.
Wait, so Amazon was pre-processing the data before feeding it to the model.
Right. They weren't just taking the raw input.
So how did they figure that out?
Well, they cleverly exploited the fact that you can submit queries with missing features.
Okay.
So by systematically omitting different features and looking at the predictions, they were able to deduce that Amazon was using techniques like one-hot encoding and quantile binning.
Wow, so they're like reverse engineering the whole pipeline,
Exactly.
not just the model.
Right. And once they figured out the pre-processing, they were able to extract the logistic regression model.
And were they successful?
Oh, yeah. 100% accuracy.
Oh,
with a very small number of queries.
And I'm guessing this was also pretty cheap because of Amazon's pricing model?
Very cheap.
Wow, these case studies are really eye-opening. I think they really drive home the point that this is a real practical attack.
Absolutely not just theoretical.
That could be carried out against real systems.
Right, even systems run by these big companies.
So clearly we need some defenses against this.
Yeah, the paper explores several possibilities.
Okay, so let's get into those. What are some of the things that people are proposing to protect these models?
Well, the most straightforward approach is to just try to minimize the information that's revealed by the API.
Okay.
So you could omit the confidence values,
Okay.
or you could disallow incomplete queries.
So you're basically trying to reduce the amount of information that the attacker can get with each interaction.
Exactly. But the problem is that this is often not enough.
Really?
Yeah, the paper shows that even if you only reveal the class label, the attacker can still use techniques like adaptive retraining.
To extract the model.
Right, so you're just making it harder but not impossible.
So what else can you do?
Well, another approach is to try to manipulate the output of the model.
Okay.
So you could round the confidence values,
Okay.
or you could add noise to the model's parameters during training.
So you're trying to introduce uncertainty.
Exactly, make it harder for the attacker to pinpoint the exact model.
So does this affect the accuracy of the model at all? It can. Yeah, there's a trade-off there.
Okay.
You're trying to balance security with usability.
Right, that's always the challenge in security, right?
Yeah. Are there any other defenses that are worth mentioning?
Yeah, the paper also touches upon differential privacy.
Okay. I've heard of that in the context of data privacy, but how does it apply here?
Well, the idea is that if you train the model in a way that preserves the privacy of the individual data points,
Okay.
then even if the attacker extracts the model, they won't be able to learn anything sensitive about the original data.
So it's like protecting the data itself, not
Mhm.
just the model.
Exactly.
So is differential privacy a silver bullet then?
Well, the paper doesn't really answer that question. It's an open area for research.
It seems like we're just scratching the surface of this problem.
Yeah, definitely. There's a lot more to explore.
So what other research directions are you kind of keeping an eye on?
Um, One area that looks promising is ensemble methods.
Okay.
So these are techniques that combine predictions from multiple models.
Okay.
And the idea is that if you extract an ensemble, you're not getting a replica of a single model. You're getting like an approximation of the overall ensemble.
So it's like harder to decipher the message if it's been encoded by multiple people.
Exactly. Yeah, it adds complexity.
Okay.
But of course, ensembles aren't perfect either.
Right.
I mean, they might be harder to extract, but they could still be vulnerable to other kinds of attacks, like evasion attacks.
Right, where you craft inputs to kind of bypass the model's intended purpose.
Exactly.
Seems like every solution introduces new challenges.
Yeah, it's a constant arms race.
Between attack and defense.
Right.
So for our listeners out there who are working with these models, what are some key takeaways? What should they be doing to protect themselves right now?
Well, I think the first and most important thing is awareness. Just understanding that this is a real threat
Yeah.
and being aware of the potential vulnerabilities of your models and the platforms that you use.
So don't assume that just because your model is behind an API or a paywall that it's secure.
Exactly. Yeah, it's like locking your front door even if you live in a safe neighborhood.
Right. You can't be too careful.
Right. And then the second thing is to be proactive, actually explore these mitigation strategies that we've talked about,
Okay.
weigh the pros and cons, and actually implement some safeguards.
So don't wait for an attack to happen before you start thinking about security.
Exactly. And then lastly, just stay informed. This field is constantly evolving.
Yeah.
So keep up with the latest research, keep up with the new attack vectors and the new defenses.
It's like continuous learning is important not just for building models, but also for securing them.
Absolutely.
So to wrap up this deep dive, you've mentioned that the paper focuses on black box attacks, where the attacker only interacts with the model through the API.
Yeah.
But what if the attacker actually gains internal access to the system,
Right. That's a whole other ballgame.
like through a compromised account or something?
Exactly. And in those cases, a lot of these defenses that we talked about might not be effective.
Right, because they're assuming that the attacker's on the outside. So this raises the question of how do we build systems that are resilient to these kinds of more sophisticated attacks?
Exactly. Yeah. Attacks that are coming from the inside.
That's a sobering thought, but an important one.
Yeah. And I think this research really pushes us to think beyond just perimeter defenses
Right.
and start thinking about deeper layers of security within these systems.
Well, this has been a really insightful deep dive. It's exposed the vulnerabilities of these systems,
Yeah.
but also highlighted the ongoing work that's being done to address them.
Right.
And I think the key takeaway is that the future of machine learning security requires constant vigilance,
Absolutely.
innovation, and a commitment to staying ahead of the curve.
Couldn't have said it better myself.
So thank you for joining us on this deep dive into model extraction attacks.
It's been a pleasure.
It's been a fascinating and thought-provoking exploration.
I agree.
For our listeners out there, we explored a paper today that showed how machine learning models can be stolen through seemingly innocent interactions with their prediction APIs. We saw how attackers can exploit seemingly benign information, like confidence values, or even the model's responses to incomplete queries to reconstruct these models with surprising accuracy.
And we saw real-world examples of these attacks against platforms like BigML and Amazon Machine Learning, highlighting the practical impact and economic consequences of these vulnerabilities.
We also talked about a range of defense strategies, from simple techniques like limiting queries to more sophisticated approaches like model watermarking and differential privacy. And we talked about the trade-offs that are involved with each of these defenses, balancing security with usability and performance.
And it really all comes down to having a security-first mindset when working with machine learning models.
Right. So be aware of the evolving threat landscape, stay informed about the latest research and defense mechanisms, and be proactive in implementing appropriate safeguards for your models.
The quest for secure and trustworthy AI is an ongoing one.
It is indeed. Thank you for listening, and until next time, keep exploring, keep questioning, and stay curious.
And as always, stay safe in the world of artificial intelligence.